Today we'll get into statistical learning theory. The goal here is going to be to provide a framework for thinking about what it is that we're trying to do when we solve machine learning problems. So at the top level, the goal of statistical learning is to draw conclusions about an unknown probability measure given independent observations drawn from that measure. So there's going to be some data generating process in the real world, and we're going to suppose that it has some probability measure that's responsible for generating those data, and we're going to try to understand something about it. And in machine learning, we'll usually be interested in the context where each datum that we get has two parts, an X part and a Y part. And the idea is that the X part is what we'll know at prediction time, and the Y part will be unknown and we'll be trying to ascertain it. For example, suppose that we have information about the color of a banana as well as its weight, and we want to know how delicious it's going to taste. So in this framework, we can call X1 the color of the banana, X2 the weight of the banana, and then package those together in a vector we call X. And we can let Y be the banana deliciousness. So we record X1, X2, and Y for many bananas, and we build a model to try to predict Y based on the values of X. But without actually conducting that experiment, we can make some guesses about how this model is going to behave. For example, do we expect the prediction function to be more sensitive to changes in X1, the color, or X2, the weight? Well, definitely the color. If you've had bananas before, you know that brown ones or green ones tend to not be as good and yellow ones tend to be better, whereas the weight is less relevant. Maybe at the extremes, like a very small banana might not be good, but generally speaking, X1 is going to have more influence than X2. So a supervised learning problem is called a regression problem if we're trying to predict some sort of quantitative output like banana deliciousness, assuming that that's measured on a continuous scale. Or a classification problem if we're trying to predict a label, which would be the case for banana deliciousness if we just summarize it as good or bad or neutral. The vector X that contains the information we'll be able to use to make a prediction is called a feature vector. We call its components predictors or input variables. And we call the value Y that we're trying to predict the response variable or the output variable. And a function from X to Y, which makes this prediction, is called a prediction function. So we haven't said how we'll come up with the prediction function. That really is the name of the game in machine learning, and all the subsequent machine learning topics we'll develop are going to be pursuing that idea. In problem 2, we'll think a little bit about how a machine learning task like image recognition fits into this framework. So it feels a bit different in the sense that the objects that we get are images, which maybe don't feel like vectors, but we can still think about them to some extent in that framework. We can certainly compute with them in that framework. Images are typically stored digitally as an array of either real numbers or vectors. So for grayscale images, each pixel is usually an integer between 0 and 255, indicating how dark that square should be. Color images are usually stored by specifying a triple of integers, indicating the red, green, and blue values corresponding to that pixel. So we can think of a grayscale image as a vector in R to the number of pixels. Or if it's a color image, it would be R to the number of pixels times 3. For simplicity, let's proceed with thinking about the grayscale images. And also, let's normalize the number here by dividing by 255 so that we get a real number between 0 and 1. So with those adjustments, the feature space is going to be a cube whose dimension is the number of pixels. And let's suppose that we have an image with 1 million pixels. The space containing the possible predictions depends on the classification problem at hand. But let's suppose that we only get pictures of cats and dogs for simplicity, so that the codomain of our prediction function is just the 2-element set with cats and dogs. So what does this look like geometrically? Well, you can't envision it because a million-dimensional space is a very strange thing geometrically. It's quite different from 3 dimensions. But we can try. We can draw a cube and pretend that it's a million-dimensional even though it's only 3-dimensional. So the probability measure on X cross Y is going to have something to do with what images of cats and dogs look like. For example, the point in the far corner of the sphere where all the values are 1 is just a solid black image. Every pixel is as dark as possible. So we wouldn't expect there to be any probability mass there. No picture of a cat or a dog looks completely black. Likewise, in the corner near the origin, the pixels will be all white, so we don't expect any probability mass quite in that corner either. Right in the middle, where every coordinate is a half, we would get a solid gray image. So really, in the whole diagonal going across from one corner to the other, we're getting a monochromatic image, and there's not going to be any probability mass there because none of those images look like cats or dogs. Also, if we select a point uniformly at random, then we get what's called white noise, which is what static looks like on a television screen. And that definitely doesn't look like a cat or a dog. So most points in this space are not going to be adjacent to any probability mass. But let's start with one picture of a cat. Suppose that we take a cat picture, look at its vector of pixels, and identify where it sits in this cube. We can say some things about where the probability mass should lie based on this. For one, we can move any pixel in any direction, so it won't be an isolated point. If you take a picture of a cat and wiggle one pixel a little bit, it doesn't change the overall impression that the image represents a cat. Also, you can perform a number of Instagram filter operations that also preserve the essential content of the image. For example, you can lighten the image, just make every pixel lighter, which moves you directly towards the white corner, and it's still a picture of a cat. So the probability mass isn't going to be concentrated at some individual point. It's going to be somehow spread out along that direction. You can also imagine that if the cat moves to a different part of the image, then lots of pixel values change. All the pixels where the cat originally was change, and all of the pixel values where the cat moves change. So that's going to take us to a totally different part of the cube. And similarly there, we're going to get some probability mass that's sort of spread out in this scaling direction and also is spread out locally because we can adjust the values of each pixel slightly without changing the essential content of the image. And for the most part, dogs don't really look like cats. So if there's a dog image somewhere, we'll have the same sort of phenomenon going on. And it shouldn't be heavily overlapping with the cat regions. And since there are so many types of dogs and cats and different ways that the images can look, we expect these regions where the probability mass is spread to somehow be highly splintered and spread out in this cavernous cube. From this point of view, what we want a classification function to do is somehow carve up this cube so as to split cats from dogs. So you can imagine kind of putting a surface, a very complex surface inside of this cube where you have cats on one side and dogs on the other. If you can detect which side a particular image is on, you can make your prediction. This particular problem is quite challenging, and most classical machine learning tasks aren't very good at it. The state of the art uses something called neural networks that we'll talk about in a couple of weeks. So in problem 3, we're asked to list an example of a real-world regression problem and a real-world classification problem. So for regression, we might want to, for example, predict a home price based on various indicators about where the home is located, how many bedrooms and bathrooms it has, square footage, and so on. And for classification, we could look to predict whether a student will be admitted to Brown University based on attributes of their application. So we need to do better than just say we want our prediction function to kind of mostly get things right or get things right as much as possible. We want to be precise about whether a particular prediction function is doing well or doing poorly. And the way we do that is we introduce a function called L, which acts on the space of prediction functions, or maybe a particular restricted space of prediction functions. And we call that a loss functional. And once we have a loss functional, we can implicitly define our best prediction function to just be the function that minimizes the value of the loss functional. And we call that our target function. So there are a couple of sort of standard loss functionals to use. For a regression function, the standard one is the mean squared error. And the reason we like to use the mean squared error is that, for one thing, it makes sense. We're measuring how far away our prediction is from the actual value, assuming that the input and the feature are drawn jointly from the distribution. So this loss functional depends implicitly on the distribution on x comma y, and that dependency is communicated here with this expectation. So the expectation needs to be computed with respect to some probability measure, and the one we take is the one that's actually generating this x comma y pair. So for example, a prediction function that misses very badly on an x comma y pair that just never happened is no problem, because when you compute expectation, you're computing a probability weighted average of the expression that you're taking the expectation of. And if h of x and y are very far apart, but there's no or very little probability mass associated with that particular x and y pair, then it doesn't contribute at all or very much to this integral or sum. Whereas for x and y pairs that occur with relatively high probability, it really matters that h of x be close to y, or else you'll have a square difference here with a decent weight being associated with it, and your loss value is going to be high. So to illustrate these points, we have problem 4, which asks us to revisit the exam scores example from the kernel density estimation section. So if you recall there, we were given this explicit density, which is shown in this with this blue heat map, indicating what is likely to happen. So students are more likely to study around 10 hours rather than 0 or 20, and their grade generally goes up, except towards the end, on average, it goes down a little bit from fatigue or something like that. So this is the model. We're pretending we know the actual distribution generating the data, and the way that we generated this data is we generated an x value according to a particular distribution, which is proportional to x times 20 minus x. So that's how it tapers off at the end. If x is smaller, x is close to 20, you get a lower density. So that's why it's light over here at these ends. But then once we know x, y is just generated according to a normal distribution with a constant standard deviation across the whole range, and with a mean equal to r of x, where r of x is this particular quadratic function that's plotted in green. Okay, so the point is, suppose we make some observations. We actually ask some students how much they studied, or maybe measure how much they studied, and then get their score and plot the pairs here. And we do it for 6 students, and we get these 6 orange points. And the question is, what must be true of the class H of candidate functions in order for the target function to be equal to the regression function? So this is the regression function in green, and it's also the target function, because it's going to minimize the mean squared error, assuming that your space of candidate functions contains this target function. So that's what has to be true of your space of candidate functions. If you insisted on using a space of linear candidate functions, then there would be some other function which does the best possible job of aligning itself with this blue smeared out mass. Notice in neither case do we pay any attention to these orange points. They're not part of this setup at this point. We're going to have to introduce them later. We're just looking at the blue mass. So the regression function and the target function are both this green curve, assuming that our space of candidate functions contains that function. So the answer to question B is no. The value of the prediction function can't be decreased by changing this green, because the point is we know exactly how these random values are being generated. And the fact that these 6 orange ones happen to all be low is just an anomaly based on our assumption in this problem that we know unimpeachably what the probability measure is that's generating these values. It's sort of like if you know unequivocally that a coin is fair, and then you flip it 5 times and it comes up 3 times heads or 4 times heads out of 5. You don't really adjust your probability at all. You are sure that it's fair, and if you're going to make bets on future flips, you're going to make them assuming 50% probability, not responding in a volatile way to whatever you've seen so far. So the last question, what is the mean squared error for the regression function? So if we use this regression function as our prediction function, we're not going to be making perfect predictions. We'll just be making the best predictions possible given this particular input data. So for example, if a student studies 12 hours, then we're going to get a vertical slice through this density at x equals 12. And the mean is going to be here, but when we actually make an observation with that x value, the score could be lower, it could be higher. There's some variance here, and the amount of variance is exactly equal to sigma y squared, this value that was posited here, because the conditional density is, as we said, a normal distribution with that particular standard deviation sigma y. what's the mean squared error? So in problem 5, we're asked to think of another loss functional for a regression problem. So one simple thing we can do is just change the squared to an absolute value in the formula. So instead of mean squared error, it's mean absolute error. This is trickier to work with because this absolute value is not differentiable. So there's an advantage to squaring from a practical point of view. Otherwise, it's a fairly similar concept. It penalizes large deviations less because you're not squaring these large values. But it's a very similar idea. Another thing we could do is decide, for example, that we don't think that the prediction function should be particularly wiggly. And we could do something like differentiate it, square that, and integrate it. So if it's really wiggly, it's going to have a lot of large positive or large negative derivatives, and those are going to contribute a lot to that integral. So in order to do that, we need to be able to differentiate the prediction function, which means we need to restrict our space of candidate functions. And this is why we have the restriction on the space of candidate functions at this point in the theory. Rather than introducing the restriction later, we do it up front because we might want to put something into the loss functional that wouldn't actually make sense for certain prediction functions. Okay, for classification problems, the standard loss functional to use is just misclassification probability. So you want to, as much as possible, get answers right. So the probability that the predicted value and the actual value are unequal is the thing you want to minimize. So this is going to be our loss functional. We'll generalize that later. But for now, let's just talk about these two. So the mean squared error for regression and the misclassification probability. So for example, we'll again suppose that we know exactly what's going on. We're going to look for the target function for the misclassification loss in the case where x is the set of real numbers and y is just 0, 1. So there's only two output values. So it's a classification problem, so we only have two output values. And the probability mass on x cross y, so you can visualize x cross y as sort of two copies of the real number line. One at position 0 and the other at vertical position 1. And we can visualize the probability mass as being spread out according to this one-dimensional density function. So it's defined in 2D space, f of x comma y, but it's spreading out the mass in a 1D way. So along this line, it's making a sort of uniform bar of mass that's like smeared out here. And along this line, same idea. And there's more mass along the bottom. So we have this 1/3 coefficient, making the total amount of mass along this bar and the amount of density at each point larger. So I tried to indicate that here just by making the line twice as thick. So this is how our probability mass is sitting in this space. Notice in this case we used the spatial dimension y to indicate this extra dimension, but we also could have used color. We could have put all of this into a one-dimensional picture, moving this bar down here and just changing it to some other color. So we'll use that visualization of classification problems more often. But in any case, the question is, what should your prediction function be? And it's exactly what you would think. If you get an x between 0 and 1, then all of the probability density along that vertical line is going to be at 0. So you're sure that y is not 1. It has to be 0. So your prediction function is going to be 0 all along here. Likewise, if x is between 2 and 3, you're going to return 1 because the only probability density along that vertical line is at this top level. In the middle, you have to think a little bit more because there's going to be probability density at the higher level and at the lower level when you make a vertical line cutting through here. But there's more probability density down here than up here. There's twice as much. When we cut through here with a vertical line, we're going to get 1/3 of our density up here and 2/3 of our density down there along that vertical line. And that means that we should predict 0 if we want to have a 2/3 chance of getting it right instead of a 1/3 chance of getting it right. So our prediction function's graph is just going to stay 0 all along here. So it's going to follow this lower bar. And then at 2, it's going to jump up and return 1 from the rest of the range. So that's our target function. So this is just what we did here. Conditioned on x being the observed value x, what's the probability of y being equal to c? You compute that for each label c, or each category C, and you pick the biggest one. So whichever one is most likely, that's the one you should return. So as long as this function is in your class of candidate functions, this will be the target function for this loss functional. Now, note that neither of these loss functionals can be computed unless you know the actual probability measure. So up to now, we've been assuming that we know exactly what's going on with the data generating process. And in statistical learning, we don't know what the data generating process is. We have to get by with just seeing observations from the measure. One thing we can do that's very straightforward to just kind of give us something is replace a probability measure with the empirical measure associated with the observations. So we put probability mass 1 over n at each of the observed points. That's the empirical measure, and we compute the loss just with reference to that measure. So that in either case, the loss functional is referencing a measure. Either in the classification case, there's a measure here on x comma y, same thing in the mean squared error case. There's an expectation in the formula, and that expectation is being computed with reference to a measure. We define it originally to be computed with respect to the actual measure, but if we don't have that, we can plug in the empirical measure instead, and what we get is called the empirical risk, or empirical loss. So loss and risk and error are just synonyms, but usually when people use the word empirical, the word risk goes with it rather than loss or error, but you could say empirical loss or empirical error. So we're going to introduce another piece of vocabulary here, which is learner. So a learner is a function which takes a set of training data as input and returns a prediction function as output. And maybe the simplest thing to do is just let the prediction function returned by our learner just minimize the empirical risk. So we don't have the actual measure, we have the empirical measure, so we just pretend the empirical measure is the actual measure, compute the loss, and try to make it as small as possible. This is called the empirical risk minimizer, and it's one example of a learner. So, as you might have guessed, that's not the end of the story, because things can go sideways. For example, suppose we have a probability measure which is uniform on 0, 1, and then conditioned on x, y is sampled from a normal distribution with mean x over 2 plus 1 and standard deviation 1. So if our space of candidate functions is a set of monic polynomials of degree 6 or less, then, so monic means the leading coefficient is 1, then given a set of 6 training observations, we'll actually always be able to fit them exactly with a unique polynomial, and that polynomial is going to be doing a very poor job. So let's plot this. The actual regression function specified in the problem is the function which takes an input x and returns an output of x over 2 plus 1. And this is what we see. So this probability mass is shown in blue here. It's got this x over 2 plus 1 ridge where it's maximal, and then it fades vertically and horizontally from there according to a normal distribution. We have our 6 training points, and the actual risk minimizer is x over 2 plus 1, because that's specified in the problem. That's the regression function. But for this class of candidate functions, we get an empirical risk minimizer shown here in purple. That's the unique monic degree 6 polynomial that passes exactly through those 6 points. So the empirical risk here is exactly 0. Every h of x minus y is equal to 0 for this empirical measure. That puts probability mass 1 over 6 at each of these red points. But what we can see here clearly is that those 6 points aren't telling the whole story. If we take into account the whole probability distribution and not just this sort of very sparse approximation of it, then we'll get a very different result. We'll get this green one instead of this purple one. And of course, no one should expect this purple one to do well on any real problem. And actually, this issue doesn't go away as we get more and more data and approximate the distribution better. It does if we keep our candidate functions at polynomials of degree 6 or less. Eventually, we'll start to get close to this green line. But if we think, okay, well, we have more data, let's use an even higher degree polynomial so it'll be more expressive. If we keep the degree of the polynomial in line with the amount of data we have, we're always going to get really crazy polynomials that sort of careen out of control and catch all these points. But do a terrible job in between. So this is called overfitting. So overfitting occurs when your empirical loss is low, but your loss with respect to the actual measure is high. So we give a name to that. We call it generalization error. It's the difference between the actual value of the risk functional and the empirical risk. And in order to address this overfitting issue, we have to introduce what's called inductive bias into the model. So for example, we can use a restrictive class of candidate functions. So we've already seen that. If the class isn't restrictive enough, it's definitely not helping us at all. In this case, degree 6 polynomials with 6 training points shows that. We can also regularize. We talked about that a little bit. We just add a term to the loss functional which says if the model is complex in a way that's described by this term, then we're going to add some value to the... You can think of it as incentivizing the optimization to avoid those complex models. And the last one is cross-validating. So we can propose a spectrum of candidate functions, and then for each one, we see how it performs on observations that were withheld from the training of that candidate function. So for example, here, we could omit one of these 6 training points, fit a polynomial on the other 5, and see how it does on that last one. And it's going to be very bad, of course. I guess that's a little tricky in this case, because if you only have 5 training points and you're fitting it with polynomials of degree 6, it won't be a unique polynomial that passes through those 5 points. So in general, you might have to think about how it is you want to set up cross-validation. There's a lot of flexibility there. The general idea of withholding training observations, training, and then checking how you did on the withheld observations, that's called cross-validation. So these are kind of our 3, at the top level, our 3 main strategies for introducing inductive bias, which is going to help us avoid overfitting. So problem 8 says, which method of introducing inductive bias does linear regression use? It's the first one. It's restricting the space of candidate functions. And what method do we use when we studied kernel density estimation in the statistics course? We use cross-validation. So we omitted 1 point and we checked how our density estimator was doing at that point. So inductive bias is not all good, of course. If we put too much of it in, or the wrong kind, then we can end up underfitting, which means that we're missing relevant considerations relating the random variables. So we end up with a training error and an actual error, both larger than necessary. So we want to kind of strike the right balance between underfitting and overfitting. And this is called the bias complexity trade-off, or bias variance trade-off. So the idea is that if you have too much inductive bias, then you'll avoid having too much complexity, so that's good, but you'll have a large error because your bias is high. Whereas if you loosen up a little bit and admit more complex models, then you might end up overfitting, but you'll be able to adapt to the data better and you won't have as much bias. So this is really at the heart of machine learning. So the kind of amazing thing about this, which is important for the purpose of being realistic about what you're doing when you're building a machine learning model, is that if you really look at the space of all probability distribution, there's actually no way to do any better than anyone else. So all learners are equal on average across all distributions. So to state this theorem in a mathematically valid way, we use finite sets. So x and y are just finite sets, and then f is a probability distribution on x cross y. So x cross y is also a finite set. So to specify a probability measure on that finite set, we just need to specify a real number for each of its elements in such a way that they all add up to 1. So that's some sort of surface in some high-dimensional space. And we can talk about the uniform measure on that surface, just like you can talk about the uniform measure on like a triangle in 3-dimensional space. So we're drawing this probability distribution from the space of all probability distributions on this finite set. And we're going to denote capital D, which stands for data, to be a collection of n independent observations from F. And we let H1 and H2 be prediction functions. So they associate a prediction for each pair D comma X. So D is a set of training observations and X is an input. So you get to see all the data and you get to see the value, the X value that you're trying to make a prediction for. You return a prediction. So H1 does that and H2 does that. So they're both learners. And we define the cost random variable we define the cost to be either the squared error or misclassification. And the punchline is that once you average over all distributions, the first cost is going to be equal to the second cost. If you have some experience with applied machine learning, this seems completely crazy because some models are definitely better than others. For example, a well-trained neural network on a wide range of problems can do a very good job compared to, say, linear regression. Or, you might have the instinct that support vector machines are very flexible. Or, people often use XGBoost as a way to fit data when they don't really have a hunch what else to use, because it seems to be very effective. And this says that actually no, if you consider the space of all distributions and just average over it uniformly, every model is exactly the same as every other model. So there's an even more startling conclusion of this, which is that cross-validation, which doesn't feel like it has any inductive bias to it. You're just saying, I want to perform well on withheld training data. You're not making any sort of explicit assumption about linearity or even smoothness. You're just saying, I want to do well on stuff I haven't seen. So this seems like there's no inductive bias there, but actually there is, because if you take the opposite approach, which you would never do in practice, but imagine, so it's called anti-cross validation. You withhold training data, and then you train your model, and whichever model does the worst on the withheld data, that's the one you go with. So again, you would never do that in real life. But if you did that, it would be exactly as effective on cross-validation, again, considering an average over the space of all possible distributions on X cross Y. And that isn't to say that these two things are actually equally effective in the real world. They're definitely not. The point is to say that real-world probability distributions have some very special characteristics with reference to the space of all possible distributions. And in a way, this shouldn't be surprising. We talked about something similar earlier when we talked about the space of all images. If you choose an image at random, it's going to be completely white noise. Whereas if you choose an image taken by a person at random, it won't be. It'll have components in it that you can recognize, or it will look like abstract art or something like that. The space of real-world images is a very, very narrow slice of the space of all possible images. And the same thing is going to be true for probability distributions. But this does have some practical benefit as we think about moving forward and studying machine learning models, because whenever we're building inductive bias into the model, we're not making some sort of practical concession that we should be ashamed of. It's absolutely essential to build inductive bias into the model if we're expecting to be solving problems in an effective way. So to recap, given a measure on X cross Y, we're aiming to predict Y from X as well as possible on average. So if it's a regression problem and the response values are quantitative, we might consider the mean squared error. And if it's a classification problem, we might consider the misclassification error. So the function that minimizes the loss functional among a given set of candidate functions is called the target function. A learner is something that takes data rather than the actual probability measure and returns a prediction function. One simple and common way to define a learner is to just minimize the loss functional evaluated with respect to the empirical measure. The empirical risk minimizer has a tendency to overfit, which we mitigate by introducing inductive bias into the model. But if we introduce too much inductive bias, then we underfit. The tension between underfitting and overfitting is called the bias complexity trade-off. Finally, the no free lunch theorem says that technically all learners are equal on average over all distributions. So the inductive bias is an essential component of effective machine learning.